Our guest today is Noam Brown. Noam is currently a research scientist at OpenAI working on planning, reasoning, and self-play in language models. As a PhD student at CMU, Noam built the first AI to defeat top humans in no-limit poker. He created Obradovic and Pluribus, which defeated top human poker professionals in human versus machine competitions. Obradovic received the Marvin Minsky Medal for Outstanding Achievements in AI. Pluribus was on the cover of Science magazine and was a runner-up for Science Breakthrough of the Year for 2019. Noam was named one of the MIT Tech Review's 35 Innovators Under 35. After his PhD, Noam joined Facebook AI Research, where he developed Cicero, the first AI to achieve human-level performance in the strategy game Diplomacy. Noam, so great to have you here with us. Welcome to the show.
Thank you for having me. It's great to be here.
Noam, before diving into today's conversation, I'd like to thank our podcast sponsors, Index Ventures and Weights and Biases. Index Ventures is a venture capital firm that invests in exceptional entrepreneurs across all stages, from seed to IPO. With offices in San Francisco, New York, and London, the firm backs founders across a variety of verticals, including AI, SaaS, fintech, security, gaming, and consumer. On a personal note, Index is an investor in Covariant, and I couldn't recommend them any higher. Weights and Biases is an ML ops platform that helps you train models faster with experiment tracking, model and dataset versioning, and model management. They're used by OpenAI, NVIDIA, and almost every lab releasing a large model. In fact, many, if not all of my students at Berkeley and colleagues at Covariant are big users of Weights and Biases. Now, Noam, in 1997, IBM's Deep Blue beat Garry Kasparov, the human world champion in chess. But it took until 2017, 20 years later, for a computer to beat the best human players at poker. And of course, that was the AI you built, Obradovic, and then later Cicero. I want to dive into about, what made chess hard, but what made poker so much harder. But before we do that, why even care about games? Why should AI be playing games? Why should we as AI researchers care about AI that play games?
It's a great question. Games have served as benchmarks and challenge problems for the field all the way back to the birth of AI. And I think there's a few good reasons for this. So one is that, it's really easy to create a benchmark that your technique is designed to address. This is like the classic overfitting problem where you develop this technique and it does really well at this particular thing. And so you create a benchmark that shows how effective your technique is. But games existed before the field of AI came along. And so these are games that, are played by humans, developed by humans. And so they're natural benchmarks that are, a little bit harder to overfit to. More importantly, games are really easy to score. It's really easy to tell if your technique is working or not. And it's really easy to compare it to other people's techniques. And it's also really easy to compare it to humans. So you have these human experts that have spent their entire lives reaching the peak of human performance in this particular domain. And so if you're able to make an AI that's able to beat these humans, then you're able to show definitively that you've achieved superhuman performance in some limited way. And I think that's like a really convincing signal. I mean, it's, I think a very common problem with any sort of research field is it's very difficult to know if you're making progress. And to have this like clear signal showing that like you're able to beat humans in this domain, I think it's unambiguous, and it makes it easy to signal to other researchers that are not as as familiar with the area that like, okay, this technique actually works well.
No, I really like what you pointed out there, that the games have been around for much longer than we've been doing AI research, and so they're very natural challenges that are not, AI researchers cannot choose them. to cater to their needs to show something off. They have to solve the problem that already exists. Now, when we think about these problems, as I said, 97, Deep Blue beats Garry Kasparov in chess. That was a big wake-up moment for the world. I think, wow, this is becoming possible. But then it took another 20 years to crack poker. Now, what made chess hard? How was that solved? But then what makes poker so much harder even?
Yeah, I mean, chess was a big deal. I mean, this took researchers decades. You know, people have been working on chess since the 50s, and the success in the 90s was a huge deal. I think the techniques that were developed ultimately were designed to succeed in chess. And I think this is one of the problems that you have when you have this like well-defined benchmark, that there's a risk that the techniques that you develop become overfit to that problem and only really succeed at that problem. And you actually see this even with Go, that the techniques that were used in chess, primarily alpha-beta pruning, was really, really effective for that domain, but wouldn't even extend to Go because the branching factor in Go is so much larger. You know, in chess, you have maybe 30 possible moves, whereas in Go, you have over 300. And, you know, that leads to an exponential blow up in the tree size. And so even getting these techniques to go from chess to Go ended up being a huge challenge, and you had to develop all these new techniques. But then even those techniques wouldn't extend to poker. And the fundamental problem with poker is that unlike chess and unlike Go, it's a game of imperfect information. So there's information that you have access to that the other player doesn't, and there's information that the other player has access to that you don't know. And you have to be able to reason about that. You have to be able to understand that if you have, you know, pocket aces, you maybe have a full house or something, the other person doesn't know that you have a full house. And so you can bet money and there's a chance that they'll call you. And at the same time, like maybe you have a really bad hand, maybe you have nothing, but you know that they don't know that you have nothing. And so you have to reason about the fact that like, okay, well, in this situation, I could still bet and make money off of them because they might fold and be thinking that I have a good hand. So that situation, that asymmetry of information doesn't come up in chess or Go, and it ends up being a huge challenge to overcome. And you know, I think one of the major challenges, and maybe the best way to understand this, is that in a game like chess or Go, the probability of an action doesn't affect that action's value. Like the value of an action is independent of the probability that you play that action. So if you open with a Sicilian defense, it doesn't matter if you do it 10% of the time or 100% of the time, the expected value of doing that is going to stay the same. But in poker, the probability of an action, the value of an action goes down the more probable it is, like the more often you do it. So for example, bluffing could be a really high expected value action, could get you a lot of value. But if you bluff too often, then the other player is going to pick up on the fact that you're bluffing a lot and will adapt to you, and the value of bluffing will actually decrease. So that is, I think, the fundamental challenge that had to be addressed in poker, and that the techniques that were developed for chess and Go were just not equipped to handle that conceptual shift.
Now, it seems like there's two related big new challenges there. One is imperfect information. You don't know the cards of the other players, and they don't know your cards. And then the fact that implies you have to play this probabilistic strategy. You should not play something deterministic because it's become too predictable and they can exploit you, right? So when I think about the algorithms that we use in AI, the fact that you're forced to be probabilistic seems a big challenge, because when I look at reinforcement learning algorithms, the standard reinforcement learning algorithms that learn from trial and error, robots learning to stand up or learn to play Go and so forth, they all tend to naturally converge onto a specific strategy. They don't need to keep a spectrum of options alive at all times and keep playing them. So how do you do that? How it seems like you can't just run standard reinforcement learning to solve poker. You need to do something else. What did you do?
Yeah, there's two ways to get around this problem. So I would actually say that there are two separate issues. There are two main issues that come up with poker. One is this asymmetry of information, And the other is the fact that you need to play this mixed strategy, we say. You need to play this like probabilistic strategy where you're randomizing what you're doing. And those end up being related, actually. They're kind of intertwined. Now, there's two ways to address this problem. And you're right that the standard reinforcement learning algorithms that are typically taught in like intro to reinforcement learning, they tend to converge to a single, action with the 100% probability. Like there's some well-defined optimal action and you converge to that and everything's great. But there's no single optimal action in poker as it's traditionally represented. So there's two ways to get around this. One is these regret minimization techniques or like self-play techniques that are specifically designed to converge to a mixed randomized strategy that is unexploitable. So I should step back and say, like, what we're trying to compute in the first place is called a Nash equilibrium. So this is a strategy where even if your opponent knows what you're playing, you will not lose in the long run. Like, I think that maybe the simplest way to understand this is with rock, paper, scissors. So rock, paper, scissors, it's a 2-player zero-sum game. You can frame it as an imperfect information game because one way to formalize rock, paper, scissors is I'm taking some action, either throwing rock, paper, or scissors. You don't observe what that action is, and then you have to take an action, either rock, paper, or scissors, without knowing what I did. So if you view it that way, it's equivalent to the way people normally play rock, paper, scissors, and you can see that it's an imperfect information game in that formalization. The Nash equilibrium in rock, paper, scissors is to randomize equally between throwing rock, paper, and scissors with 1/3 probability each. Because if you play that strategy, then even if your opponent knows that you're doing that, there's nothing they can do to beat you in the long run. If you were to play 1 million rounds with this strategy, you're probably going to break even in the long run. Now, I should say, like, this Nash equilibrium obviously is not going to lead to you winning an expectation in it. But, we're using this as a simple example. When you go to a more complicated game like poker, it's if you're playing the Nash equilibrium, it's actually really difficult for the other player to figure out how to counter that. And so you'll end up guaranteeing that you're not going to lose an expectation. And also in practice, you'll end up winning an expectation because your opponent will make mistakes in how they're countering your Nash equilibrium strategy. And of course, if both players play the Nash equilibrium, then they'll both break even in the long run in expectation. Okay, so that's what we're trying to approximate. We're trying to approximate this Nash equilibrium strategy that guarantees in the long run we will not lose in a 2-player zero-sum game. Now, the way we do that, the simplest way to do that is with something called fictitious play. And it's actually a surprisingly simple algorithm. So in rock, paper, scissors, what it boils down to is like you start with some random arbitrary strategy, like maybe always throw rock. And then you look and see like what is the strategy that would do optimally against that strategy. So if one player is always throwing rock, then the optimal counter to that is to always throw paper. And so that's the second strategy. And now you're going to take the average of those two. And your new strategy is 50% rock, 50% paper. And now you look at, okay, what's the strategy that does optimally against a player that's throwing rock half the time and paper half the time? Well, the optimal action in response to that is to always throw paper. And so now you're going to update your strategy as like the average of always throwing paper, and always throwing rock. So you're taking the average over, all the different strategies that you've played so far. So now you're throwing 2/3 paper, 1/3 rock. And now again, you look at what's the optimal response to that? Well, the optimal response to that is to throw scissors. And so now you're doing 1/4 scissors, 1/2 paper, 1/4 rock. And if you keep iterating in this way, you will actually converge to 1/3 rock, 1/3 paper, 1/3 scissors. You'll converge to the Nash equilibrium in the long run. Now, the way it does this is called fictitious play. It's very effective. It ends up being kind of slow, especially in really large games like poker. And so we end up using more sophisticated versions of it. The one that we're using in Libratus and Pluribus is called counter-factual regret minimization. But in the long run, it will get you to the same endpoint through a similar process, this self-play, having one agent play against the other and figuring out how to beat all the prior strategies. It will do something similar to that. It will just get there faster.
This is really interesting, Noam. Now, for rock, paper, scissors, it's clear from your explanations and problem many people knew ahead of time. Equal probability on all three of them makes it impossible to beat you. Now, it sounds like you're saying poker has a similar thing. It's a bit more complex, but can you still analyze it? When your system is done learning, can you look at it and say, for example, when Librados or Cicero has pocket aces in, let's say, a heads-up Texas Hold'em situation, can you inspect it and ask it, what with a pocket aces, what's the probability of, let's say, raising or folding? I mean, does it even have a probability of possibly folding when it has pocket aces? Like, can you inspect that and get an intuition of what is the optimal way to play?
Yeah, absolutely. And so what you'll end up with is, you'll end up with a strategy that's like the average over everything you've done. And as you keep iterating, it will converge to the Nash equilibrium. And so you'll have this strategy, and you can inspect and say like, okay, well, what should I do if I have pocket aces? Well, look at all the previous iterations that you've done. Look at all the times you've been in a situation where you had pocket aces, and what did you do in those prior strategies? And interestingly, there will be like some really, really tiny, vanishingly small probability that you will fold pocket aces, because on the very first iteration, the bot had no idea what it was doing, and so it would just play completely randomly. And so there was like a small probability that would fold pocket aces on that very first iteration. It quickly realizes that that's a bad idea, and it will not do that in the future iterations. So now I should also caveat this by saying, like, okay, rock, paper, scissors is a really tiny game. You're going to encounter all the states that you could be in a really tiny game every iteration. But when you're going to like a very large game like poker, there's 10 to the 161 different decision points that you could encounter in a game of heads up, no limit Texas Hold'em poker. You're not going to encounter all of those situations during self-play when you're having these two bots play against each other. And so you need some way to generalize between similar situations. And the way you do that is there's actually a few ways you can do it. We didn't use neural nets in Libratus and Pluribus, but the best way to do it is actually with neural nets. And so you can, when you find yourself in a situation, like maybe you have pocket aces and the board came out like 5, 8, 9 of hearts, and you're trying to decide what to do, and you've never encountered that situation before, what you're going to do is, leverage the fact that you've been in similar situations before. And so you can interpolate between those similar situations, understand like, okay, well, I was in this similar situation before, I was in this other similar situation before, this is what I did in those situations. And you can interpolate that to figure out what should you be doing in this particular situation.
Now, neural nets can help you with that interpolation. I'm wondering, when you talk about essentially playing the average of everything you've done in the past, that's how you're going to get to the Nash equilibrium, do you actually have to keep all these past games around to go effectively look up what the average is? Or can you use a neural network to, in some sense, compress all the past games and automatically tell you in some summarization way, in this situation, this is what you did this fraction of the time?
That's a great question, yes. So, essentially, yes, you can use a neural network to approximate that. And that's actually, so we have this paper called Deep Counterfactual Regret Minimization. This was the first regret minimization, like counterfactual regret minimization adaptation to deep neural nets. And the way we do it is we use two neural nets, one that is generalizing between similar situations, understanding, okay, on the current iteration, what should I be doing in these novel situations that I'm encountering based on what I've done in the past? And then also we have a second neural net that is approximating, okay, given what my strategy has been over all of these previous iterations, what is the average over all these different situations? Like trying to compress that average into a single neural net. So you don't have to you find yourself in a novel situation, you don't have to go back through all the previous iterations and figure out what you did in those. You can just use the neural network that's approximating that average for you.
We'll get to this later, but almost like large language models compress everything that's written on the internet, this neural net is compressing everything that's in your past gameplay and can re-summarize it for you. Now, one thing I'm curious about, Noam, is when you think about the game of poker, you talk about this Nash equilibrium convergence. If we think about chess and Go, a big part of it is search. You say, in the current situation, what can I do? What can my opponent then do? And you try to figure out what's the possible sequence of things that could happen, and from that, decide your current move by anticipating the possible futures, and then choosing the direction that gives you the best possible futures. In poker, does that play a role too?
Absolutely. And I think a lot of people find this surprising. And in fact, I found it surprising when I first started studying poker and understanding how the game really works at a high level to do research on it. Being able to plan ahead in poker is actually a critical part to success. And it's a bit counterintuitive because, there's like this question of what does it mean to plan ahead in poker? Like in chess, it's very clear. You say, okay, if I move my bishop to this square and then, my opponent is probably going to do this, and then you can see what the board is going to look like after those sequence of actions. And you can understand whether that's a good board state for you or a bad board state. But what does it mean to plan ahead in poker if you don't even know what your opponent is going to do next because you don't know what their cards are? So I want to get to that. I guess I should take a step back, and I want to emphasize that search is extremely important for being successful in these games. And it's not just true for poker. It's actually been extremely true for chess and Go as well. I think it's something that has been underestimated in the AI community for a long time. But what I mean by search is this leveraging extra computation at test time. Like when you're actually playing the game, instead of just acting instantly, you try to scale the amount of computation that you're doing in the moment in order to achieve better performance. That's what I mean by search or planning. And if you look at Go, I think this is actually Go. You can see the results quite clearly. There was this paper that came out on AlphaGo 0. So this DeepMind created AlphaGo, which beat Lee Sedol. This was a landmark achievement that happened in 2016. And they follow this up with like an even stronger version of AlphaGo called AlphaGo 0, which learned to play the game completely from scratch without any human data. And so they showed, the full version of AlphaGo 0 with this the search algorithm that they're using called Monte Carlo tree search, that achieves an ELO rating of about 5,000. Now, expert human players are around 3,600 ELO. So to achieve 5,000 ELO is way, way beyond what any human could possibly achieve. I mean, we're talking, to give some context, I think like an ELO gap of 100 points, like if you're 100 ELO points above somebody else, then that means that you're expected to win 2/3 of the time. So to be 1,400 ELO points above another player means that you're just like always going to win. But if you take out the Monte Carlo tree search at test time, that is the search that it's doing at test time when it's actually playing the game, and instead just have it act according to its raw neural network, raw policy network, the ELO rating drops to around 3,000. And so you need to have this planning process. You need to have this tree search process in order to achieve superhuman performance in Go. And even today, nobody has made a superhuman Go bot that doesn't use some kind of search. Even at test time. Forget about training time. Even just at test time, you need some kind of search to achieve superhuman performance in Go so far. Now, I think a lot of AI researchers hear this and their natural response is like, well, surely we could just scale up the training, scale up the neural net, and we could achieve superhuman performance in Go. And that's true. If you scale up the amount of training that you do and you scale up the size of the neural net and the training time, you could eventually overcome that gap. So you could get back to 5,000 ELO. But there's a question of like, okay, well, how much would you have to scale up by? Like, how much is this Monte Carlo tree search buying you? And so the answer is, in order to get the raw neural net from like 3,000 ELO to 5,000 ELO, you would have to scale up the training and the neural net size by 100,000x. So adding Monte Carlo tree search at test time, and to be clear, by Monte Carlo tree search, I mean this thing where it's like planning ahead, saying like, okay, if I do this, then the other player is going to do this, then I'm going to do this, and then, I'll be in this board state that looks quite good for me. That process is getting you the equivalent of scaling up the neural net by 100,000x in Go. And that's just if you do it at test time. I'm not even talking about, like I should say the neural net itself is trained using Monte Carlo tree search during training time. So if you were to take out Monte Carlo tree search at training time as well, I don't even know what the number is, but you'd have to scale up by like orders and orders of magnitude in order to do this without any search. And yeah, so I think that really shows just how important search is. Now, when you go to a game like poker, the story is actually quite similar. And we actually did a man-machine poker competition in 2015. So I should say, we for a long time, researchers were not doing search in poker for a variety of reasons. Like partly because we didn't really understand how to do it in poker. It's like not as easy to figure out what does it mean to do search in poker compared to a game like chess or Go. And also because I think people didn't really appreciate how important it was to achieve superhuman performance in these prior games. And so we, in 2015, there was this event called the Annual Computer Poker Competition where all the different research labs that would work on poker AI would get together. They'd all play their bots against each other and, see who wins. And our bot from Carnegie Mellon actually won that year. And so we decided to do a man-machine poker competition with our bot. We thought it might be superhuman and play against the world's best players. And it ended up losing by a pretty wide margin. But what we found, what I noticed during the competition is that the way the humans were playing was very different from how the bot was playing. Like the bot had been training for months trying to get better and better at poker, but when it came time to actually play against the humans, it would just act instantly. Whereas the humans, when they were in a difficult situation, they would sit there and they would think. And they would think for, maybe a few seconds or maybe a few minutes, but they would think as long as they needed to in order to figure out what should they be doing in this particular situation. And then they would be able to make their move and be successful. And so that made me appreciate that, humans are doing search in poker, and it might be the key missing ingredient that would enable us to achieve superhuman performance. And so I decided to investigate, how much of a difference does it make to do search in poker? And I'll get a little bit, I'll get to how you actually do that. But I decided to investigate how much of a difference does it actually make in poker. And, what I found is if you add search just on the final round of poker, so there's 4 rounds of poker, there's the pre-flop, flop, turn, and river. If you just do search on the river, that is the equivalent of scaling up your training and the size of the model by 100,000x. And again, so that's and I didn't know about the Go results at the time, about how much of an improvement it was adding search to Go, because that paper hadn't been published yet. But what we found in poker was that adding search on the river increased the performance by the equivalent of scaling up your model by 100,000x. And that blew me away, because over the course of my PhD up until that point, 3 years of my PhD, I had managed to scale up the models and scale up the training by, 1 or 2 orders of magnitude, 10, I think it was about 10 or 100x. And that was, I thought, a very impressive achievement, to go make these things 100x better, 100x faster. But that was just nothing to adding search. Adding search, you get 100,000x improvement. And so it made me appreciate that, I everything that we were doing up until that point was just going to be a footnote in my thesis. The only thing that really mattered was adding search. And so when I saw that result, the whole research paradigm changed. It all became about adding search. And I spent the next year just working basically nonstop trying to scale up search in the PokerBot. We did another man-machine competition in 2017. And that time we won by a huge margin. And I think almost entirely due to adding search.
That's so interesting, Noam. So how do you run search? Because if I'm going back to what you said earlier, finding the Nash equilibrium meant finding this probabilistic description of essentially for every situation, what's the distribution over actions to take. It's not so clear how you connect that to search, because usually search ends up with something where you say, how good is the situation I end up in? It doesn't end up with a probability distribution over actions in the final situation.
Yeah. Okay. So this is where it gets a little tricky, and the truth is that it actually is quite difficult to do search in poker, and this is why it took so long. I did. You asked previously, why did it take 20 years after Deep Blue beating Garry Kasparov for us to beat humans in poker? And I think the answer is because figuring out how to do search in poker ended up being trickier than people expected, and also because people weren't investigating it that much because they didn't appreciate how much of a difference it would make. So there's actually two ways to do search. I'll cover both because they're actually quite different. One way is you've computed an approximation of the Nash equilibrium up until, for the entire game. This is using your self-play techniques where you've had the bot play against itself for, trillions of iterations. Obviously, the game is not big enough. It is too big to store the exact strategy. And so you have to rely on this neural network generalization to store the policy for the entire game. Now, that ends up being a problem because, your neural net is not perfect. It doesn't have perfect function approximation. So there's going to be errors in that approximation, and those errors really do matter. And so what you can do is when you get to the later parts of the game, you can say, okay, let me assume that everybody's been playing the Nash equilibrium up until now. There is some probability distribution of what the other player's cards are. There is some probability distribution over what they think my cards are. That defines its own subgame at this point, right? Like you can imagine this like subgame where my distribution of hands is no longer uniform. Like in poker, it usually starts out as uniform, but it doesn't have to be uniform. And so you can imagine this like, mini poker game where now it's no longer uniform. It's like whatever the distribution is if we both played according to the Nash equilibrium up until now. And now we're just going to, now we've like defined this self-contained subgame. We can solve this at test time. So when we're actually in the middle of a hand, I can say, okay, well, there's like, 4 actions left in this game. I know what the distribution is over my cards. I know what the distribution is over your cards. It's common knowledge. Let's just compute the equilibrium now for this subgame. And then you can play according to that policy. Now, there are some minor challenges that come up when you try to do something like this. The exploitability question of like, how do you ensure that what you end up computing is a Nash equilibrium? Like you're computing a Nash equilibrium in this subgame. How do you ensure that it's also a Nash equilibrium in the original game? It turns out if you add entropy regularization, that's the easiest way to address this problem. So you're kind of biasing the equilibrium solution to being close to uniform. If you add a little bit of that, then you can actually ensure that this will be a sound strategy that you can play in the full game. So that is intuitively the way to do it. Now, this ends up being a little tricky because I said, you're close to the end of the game. There's only 4 actions left. If you're earlier in the game, it ends up being tricky because you have to, in chess, we have what's called a value function, right? So if you play out 4 actions, like, okay, I'm going to move this piece, my opponent's going to move this piece, so I'm going to move this piece. You're not at the end of the game yet, but you can still stop there, look at the board, and have a sense of who's winning. And that's the value function. So in AlphaGo and in Deep Blue, you have these functions. In AlphaGo, it's a neural network where you plug in the board position, and it will tell you the probability of each player winning. In poker, that's tricky because, like, what do you feed into your value function? You don't know, like, do you feed in, your cards? Do you feed in, you don't know the opponent's cards. You can't feed in the opponent's cards. If it's one thing if you reach the end of the game and then the game is over, like that's easy to evaluate, at least during self-play. And so what it turns out what you need to do is feed into your value function the probability distribution over what you think the other player's cards are and what they should think your cards are, given the Nash equilibrium policy that you're assuming both players are playing. That's a bit counterintuitive, because it kind of changes the notion of a state. Like, I don't want to go too far, off the deep end with you here, but like, in standard RL, like, in chess, like what does it mean what do you actually care about? Like, what is the state in a game of chess? Well, the state is the board, and that's really easy to represent. But in poker, what is the state? Like, the state has to be all the information that you need to make the optimal next choice. But just knowing the cards that you have and the actions that have occurred is not enough information in poker to really define the state, because it depends on something less observable. It depends on the beliefs of the players, right? Like, if I have a really bad hand, the value of that situation could be, the value of having a really bad hand could be really bad. But if the other player thinks that I have a really good hand, then the value of that situation is actually quite good, right? Like, if I have a busted straight, but the opponent thinks that I have a straight, then I actually have very high expected value right now. And so in order to determine the optimal next move, and in order to determine the value of a state, you need to condition on the beliefs of the players as well. And so that is conceptually, I think, a very tricky thing to wrap your head around, but it's actually really key for understanding how to approach the game of poker compared to a game like chess or Go. And I think more broadly in real life as well, it's a really important conceptual thing to wrap your head around, that the notion of a state can include things like beliefs, because in the real world, there is no perfect information. People have access to different amounts of information, different information, and you have to account for that when you're deciding what an optimal path forward is.
Now, that's really interesting to me, Noam, and surprised me a little bit, though, with your explanation. Now, it doesn't surprise me as much anymore, but the fact that you, even for your own cards, your own hand, you don't just pass on what's the hand, but you also pass on to the neural network what all the other players think your hand could be, the distribution over that, and you have to model that too. It's not enough to just pass on your own cards into the neural net. Now, one thing from, I haven't played a whole lot of poker, but I play poker sometimes, and one strategy, but I guess it's very different for these AIs, is you play, in some sense, you play without bluffing. You play very straight up for the beginning of the evening. And so you build up the belief in other players that, this person's not going to bluff. They're always like, whenever they go in, they have the cards to back it. And then later you can start exploiting that a little bit, of course, not too much, because then it'll backfire, but you can then have a threat to other players in the sense that they thought, well, he probably has something real because the whole evening that's been the case whenever they put this much in. That aspect, as I understand it, doesn't really exist in any of the AI players. This notion of modeling a player over the course of an evening, that you assume always the same model. You assume every player is a Nash equilibrium player, right? Which is very interesting to me, because it seems like, especially when you go to larger tables where it's not just heads up, but it's, let's say, 6 or more people at a table, sometimes you, maybe not with the pros, but in casual games, the way you do well is you start understanding certain players that are playing highly suboptimal, and you exploit them because you understand their suboptimality and how they play, right? And it seems like that's something that the AI players you build didn't have and didn't need to have to even win the big tables. Is that right?
That's right. And I think a lot of people, including ourselves to some extent, found this surprising. I remember when we announced Libratus and that we managed to beat top humans in heads-up no-limit poker. That's 2-player no-limit poker. A lot of people were saying, like, well, that's great, but it's not going to extend to 6-player poker because, you run into this notion that, like, there's no more minimax equilibrium, that the minimax equilibrium is no longer meaningful. You have to account for opponent styles and exploitation. And it turned out the answer that was that you can take the same techniques, you have to scale them, you have to figure out how to do, clever things to account for, like, the much larger game. Like, 6-player poker is obviously a much larger game than 2-player poker because there's, like, this exponential blow up in the sequences of actions that can occur. But the the challenge of like having to adapt to the other players and account for the fact that they're trying to adapt to you, that ended up actually not being a critical part to achieving superhuman performance. And I think I think there's two lessons there. One is poker is an unusual game, and the fact that you can get away with not modeling other players in poker does not mean that modeling other players is not important in general. I think it is, and we actually observe in diplomacy that modeling other players is really critical to success in that game. So I think partly it's just a quirk of poker that you don't need to worry about this opponent modeling aspect in order to do well in 6-player poker. The other thing is that these regret minimization techniques, I described earlier this fictitious play algorithm, and like the techniques that we're using are called more broadly regret minimization techniques that converge to, I said they converge to a Nash equilibrium. That's really only true in 2-player poker. That it's only guaranteed to converge to a Nash equilibrium in 2-player poker. Outside of 2-player zero-sum games, it converges to this equilibrium concept that I won't really go into. It's called coarse correlated equilibrium, but it ends up not being that meaningful. But it turns out that that's a theoretical guarantee, and in practice, it ends up doing quite well regardless. And that, I think, is a general truth that even though these techniques are only guaranteed to really do it, give you guarantees of not losing an expectation when you're playing a 2-player zero-sum game, in practice, they do quite well even outside of that paradigm and more broadly. Now, I do want to emphasize, though, I think opponent modeling and player modeling more broadly is actually really important. In general, it was not necessary in poker in order to achieve superhuman performance. I certainly think that you could do a lot better if you were to model the other players. It's just that the techniques that we had weren't really that strong to do it, and it wasn't necessary. But it did end up being necessary in diplomacy, and so we developed techniques to do opponent modeling in diplomacy. And I actually think that those techniques would carry over quite well to poker. So I think it would be interesting to try that and actually try to do that in poker now. And it's just there's been higher priority items to focus on, especially with the emergence of large language models and a lot of interesting research to do there. It's not something that I've been working on, but I do think it would be interesting to see, like, how strong can you make a poker bot now that adapts to other players and accounts for their suboptimal play. I think you could actually make a really strong poker bot that would exploit weak players.
I'd love to switch to diplomacy and large language models soon, Noam, but I have a couple more questions about poker I want to ask you. The first one is, when playing poker, you play one round essentially. Cards get dealt, you play, somebody wins, but then usually you don't just play one round, you keep playing till only one person at the table has any chips left, right? And so is there a difference between optimizing for an individual hand and say, I want to play optimal for this hand, versus I want to play optimal to optimize my chances to win the table? And the reason I'm bringing this up is because I think about my own play, and maybe it's flawed, but I tend to think the larger the table is, the more important it is to early on accumulate an advantage and collect the chips from the weaker players, because once you get to the heads up, you need to be ahead, and it's maybe better to have, and given there's so much luck involved, it's maybe better to play a bit more risky and have a chance of being the one that comes out with a larger stack of chips with some chance, but also a high chance of just busting out, rather than being the one that stays in the middle and has the middle number of chips at the table and then ultimately loses anyway against the one who has the biggest stack.
Yeah, that's a great question. So there's two main versions of poker. So one is tournament poker and one is cash game poker. So cash games are, you buy in with $10 or $100 or whatever, and you can cash out whenever you want with however much money you have at the table. And that's the version of poker that we were focused on. The other version of poker is tournaments, where you buy in for a fixed amount and you play until only one player is left. And then there's some payout structure depending on if you finished first or second or third. There are a few added complications when you look at tournament poker, but it's actually not that difficult to overcome. It ends up being a little bit more difficult to score because you have to play, if you're playing in a cash game and you want to evaluate how good is your bot in a cash game, well, you can look at each hand individually and say like, okay, well, I've played like 10,000 hands. How much money has the bot made in expectation over, how much money has the bot made over those 10,000 hands? If you want to evaluate how good your bot is in a tournament, you have to play whole tournaments to get one sample. And so you might have to play like 100 or 1,000 tournaments in order to get a statistically significant measure of whether your bot is actually good, because poker is a very high variance game. I think a lot of people don't appreciate just how high variance poker is. Like, you can play poker for a full year and make money and actually be a losing player because you just got lucky. It's really like the highest variance game that people play seriously. And so that's the main reason why we just, didn't really focus on tournament poker. The added complications of like, you don't view each hand individually. You have to view it as like a sequence of hands. It ends up actually not being a big problem in practice when you use neural nets, because in a cash game, the reward at the end of a hand is how much money you won or lost in that hand. And now in tournament poker, you just have to modify that to be like, okay, what's the probability that I end up winning the tournament or losing the tournament? That is a totally fine signal. It's just like you're going to need a lot more samples now in order to learn how to play tournament poker. But it's definitely an addressable thing that we know how to address.
Last question before we switch to diplomacy and language models and so forth. Did you ever consider, I imagine not, but I got to ask, did you ever consider just quietly running your bot? Is that even allowed? Can you run your bot and, is that how your bank account gets filled right now? You have your bot just running, playing online poker, and that's just, passive income you're just earning while we're talking here.
I definitely thought about it at various points during my PhD. I've been approached by various shady or less shady organizations asking me to supply them with the poker bot that they could use to run online. It's not a good idea for several reasons. First of all, the code is the property of CMU, so it's not my place to run that. I mean, I could probably just code it from scratch and do that, but there's still a laundry list of issues with that. One issue is that I think, the poker sites invest a lot in combating poker bots. So they have all these like different security mechanisms to like make sure that the people that are playing are playing honestly without the use of assistance software. So they'll, see what programs are running on your computer. They'll also like look and see like, is the person playing in a style that's very similar to how a bot would play? Because like you can compute these bots. It's kind of like we observe this a lot with AI, that you can train these systems totally independently and they'll end up converging to similar things. And so you can compare like, okay, if this person is playing in a way that's very similar to how the poker bot's AI says that an AI would play, then you can like flag that as questionable. And you can like, what they'll ask you to do, and this happens sometimes. And so they'll ask the person, we want you to prove that you are able to play poker this well with a camera in your room now. So we want you to record yourself playing poker with a camera, and we want to make sure that, there's no other AI assistance software helping you out while you're playing. If it's a really serious case, they'll actually insist, they'll freeze your account and say, in order to unfreeze it, you have to come to our office and play poker here to prove that you are as good as we're observing.
Oh, wow.
Yeah, there's like other, red flags that they can observe. So for example, if somebody's like repeatedly withdrawing money from their account, then that's a sign that they might be running, a bot, because poker players don't usually withdraw money from their accounts. They usually just like leave it in there until they lose it all. And so if somebody is like, constantly withdrawing money, trying to keep their bank account minimal, because they're afraid that they might get flagged as a bot and have their account frozen, then that's a sign that they, might be suspicious. So there's a lot of risk with running this kind of operation. The other thing is that it's actually pretty difficult to be profitable playing poker these days. People have gotten so good at poker, and a lot of the weaker players have dropped out of the game because the field has gotten so strong that the margins have gotten a lot smaller. And so I think there's not as much money in online professional poker as there used to be. And the other thing is, just from a career standpoint, I decided that that's just not what I want to do with my life. I mean, I think we're in a really special time that, AI research is I couldn't imagine doing anything else. I think I really hit the jackpot with my career. I love what I do. I want to keep doing research, and fortunately, it actually ends up paying pretty well. So I don't think that it would actually be a more profitable thing to, just leave all that behind and try to run poker bots as a full-time business. So I have no interest in running poker bots online. Never got into that, and I don't see that changing.
That's so interesting. Thanks for sharing. All the non-AI aspects are very interesting to me too. All the security measures they're taking. Now, switching gears from poker, you then moved on to working on AI for the game of diplomacy. Probably not as well-known a game for everybody. So maybe you can explain, what is diplomacy? Well, from there, what were the challenges and what did you achieve?
Yeah, after Pluribus, so we announced Pluribus in 2019, so that was a 6-player poker bot. We were deciding what to work on next, and we wanted a game. Well, we wanted a challenge problem that would just be equally impressive if we were to succeed in that challenge. It isn't easy to figure out what that could be. I mean, and the motivation for this is that if you look at the history of AI, I mean, chess took decades for AI to solve. Go took another 20 years. Poker took decades. But the pace of AI progress had been progressing so quickly that it wasn't really clear what a similar challenge would look like. People had proposed various games before. So there was a paper that came out proposing that this cooperative card game called Hanabi be the next challenge problem because it's a cooperative game. Turns out that ended up, being solved. We actually managed to make a superhuman AI for it in 6 months. And then there was, a lot of people were looking at StarCraft and Dota 2. OpenAI worked on Dota 2 and DeepMind was working on StarCraft. Both of them succeeded within a couple of years. And it became clear that, if we really wanted to have a truly impactful result and something that was not addressable using existing techniques, we had to think really ambitiously. And so we landed on the game diplomacy. And there were a few reasons for this. So diplomacy is this natural language negotiation game. The way the game works, there's 7 players. It's kind of like a mix between Risk, the board game Risk, the TV show Survivor, and the card game Poker. And you have these complex negotiations that go on where the only way that you can win is by convincing other players to work with you. So most of the game actually takes place in some back room where you're talking one-on-one with this other person, trying to convince them to work with you. And so every turn consists of 15 minutes of these one-on-one negotiations happening in private between all the players. And then after that negotiation period, everybody will write down what their moves are and execute them simultaneously. So, you promise people that you'll do something, and then when you actually write down your moves, there's this big question mark of if you're actually going to follow through on that. Now, the way the game works, it takes place at the onset of World War I. So you play as one of the 7 great powers of Europe, England, France, Germany, Austria-Hungary, Turkey, Russia, and Italy, and Germany. And the way you win is by controlling a majority of the board. Now, in practice, that rarely happens because if somebody actually ends up gaining coming close to half the board, controlling half the board, then the other players will realize what's going on, team up with each other, and stop that from happening. But in practice, you get a score that's proportional to how much of the board you end up controlling at the end. And the only way that you can win is really by working with other players. And so we thought that this would be a really interesting game to look at because so much of the gameplay is happening in natural language negotiations between these players. And on top of that, the conversations are not public. Like, these are not happening at the game board. These are actually happening in private between these players. And so you have to reason about, what are these conversations that the other players are having behind my back? Are they conspiring against me without me knowing? And then also, like, the moves are happening simultaneously, so you have this imperfect information aspect in the moves. And then also a big part of the game is the human nature to it. The fact that humans are not perfectly rational, and you're playing with somebody that has these very, very human emotions, that if you backstab them and betray them, they're going to get really angry at you and spend the whole game trying to get back at you. Like, that's not something that a bot necessarily would do, but it's something that the bot has to account for if it's playing with a human. And so all these like human modeling aspects come into play when we didn't really see that being necessary in poker. And so for all these reasons, we thought, if you can make an AI that could actually play diplomacy and beat humans at it, then that would be a really surprising and cool achievement, and we would learn important lessons along the way. So that's why we chose diplomacy. And it also felt like a good time because, in 2019, you had GPT-2 come out. There was a lot of progress with language models being made. And we felt like, whereas before diplomacy was like viewed as this impossible grand challenge, it was suddenly more achievable. I mean, people had been working on AI for diplomacy for a long time. It was proposed as a benchmark all the way back in the 80s, actually. But the thought that you could play the full game of diplomacy in natural language was just like, outrageous. And we felt like in 2019, we thought it would be very difficult, really surprising if we succeeded, but it wasn't out of the realm of possibility anymore. So that's why we chose diplomacy.
Fascinating game. And actually, personally, I've never played that game, but I remember as a kid, probably 10 years old, browsing through possible board games to purchase. And diplomacy, I remember reading the rules and descriptions and being like, that sounds like an amazing game, but this is before video games. You had to play it as a board game. And I was like, I don't know if I can ever find 7 people to play this game, because it's a game that plays for a long time, right? You can play for hours and hours. And my parents were like, yeah, we're not playing this game, but I'm glad that now this game is in my life in some sense, finally.
Yeah, I mean, it's definitely like, it's a game that usually takes about 6 hours to play. And, because of that, people get really invested in it. You can be allied with somebody for 4 hours, working really well with them, and then all of a sudden they backstab you on the and completely ruin your chances of winning. And, that really hurts at an emotional level. So people take it very personally. And so it's not an easy game to play. A lot of people really dislike it for this reason. But it is a unique game in that respect. I would describe it as a game that is as close to real life as you can get.
Now, what did you do to crack it?
Yeah, so we approached diplomacy. So we decided to start with a simplified version of diplomacy where there's no natural language communication, just focused on the moves in the game. And that ended up being a surprisingly difficult challenge on its own because, again, in poker, you just compute the Nash equilibrium or approximate it, and you end up achieving superhuman performance. We actually found in diplomacy that ends up not being true. If you just train a bot completely from scratch with no human data in diplomacy, you will not achieve superhuman performance. And that actually surprised a lot of reinforcement learning researchers. I think there was this notion that because this paradigm had worked so well for chess and Go and poker, that it could work for any game. But that's actually not the case. And intuitively, the reason for this is because the bot ends up getting really good at playing with other copies of itself, but not understanding how to play with humans. It's as if you had trained a bot. Imagine you train a bot completely from scratch to navigate, traffic in the U.S. Without any human data, and it might learn to drive on the left side of the road. That's a totally reasonable equilibrium for it to arrive at. If all the other drivers are also driving on the left side of the road, then it works out fine. But if you then stick it in a situation with real human drivers in the US, it's going to crash and it's going to do terribly. And similarly, you can imagine in a negotiation game, if you were to train a bot completely from scratch without any exposure to English, it will learn to communicate. It could learn to communicate, but it would learn to communicate in some gibberish robot language that isn't how humans communicate. And so when you stick it in a game with a bunch of English speakers, it's not going to do well. So I think this is actually one of the most important takeaways from the diplomacy work, that in order to do well in these not two-player zero-sum games, in order to do well in games that involve cooperation, you have to have human data if the game is sufficiently complicated. And that's actually, like, I think it was not the majority opinion in the multi-agent AI space for a long time. I still don't know if it is, but it's something that I feel very strongly is the case, that if you want to achieve cooperation with humans, then you need to use human data if the domain is sufficiently complicated. So that's, I think, one of the major takeaways. And the way we accomplish this in diplomacy is by leveraging human data. So we found that if you bring, we found this giant data set from a website called webdiplomacy.net, where they've recorded all the games that people have played on the site for the past 20 years. So we trained a model on that data to imitate how humans play, and then we combine that with self-play. So basically what we do, okay, so this is like still ignoring the language aspect of the game. Just looking at moves in the game, we're trying to play this version of the game where players don't communicate in natural language. We still want to do well. What you could do is like take these games, do supervised learning on it. So try to create this like model of how a human would play diplomacy, and then stick our bot in a game with 6 of these, quasi-human players, and try to figure out how to beat them. So essentially you train a best response to the human supervised learning models. This ends up not doing very well because you end up overfitting. And this is, I think, a classic reinforcement learning problem where you just like, you don't have enough data. You end up overfitting to the quirks of your, virtual setup. And the way we got around this is, I think, actually quite similar to how a lot of RL researchers get around this, is with regularization. So we found that if we add search and improve, like we kind of have the other players, like we have this model of the human players that's trained through supervised learning on human data, but then we also add search to it so that it can adapt to our strategy. We find that makes our strategy more robust to the players not playing exactly according to the supervised learning model. And when we then take that model that's played with these like search-based human imitation models, and we play with real humans, then it ends up doing a lot better. So that's one of the techniques that we used. And we end up doing that for the non-language version of diplomacy. We also end up using that for the full natural language version of diplomacy. So that's the non-language aspect. And then the language aspect, there's a lot going on there. So, first, how do we even have the bot learn to communicate with the other players? We, in addition to like the moves in the game, we also have all the dialogue that the players have said to each other in this giant data set of like 20 years of human games. So we first take a pre-trained model trained on like general internet data, and then we fine-tune it on these games of diplomacy. And so we end up with the bot that can communicate in like a very human-like style in talking about things in diplomacy. The problem is that this ends up not being very grounded to what's going on in the game itself. So we can say things like, "Oh, I'm going to support your unit from A to B," when the other player doesn't actually have a unit in A. So there is this disconnect between like what's going on in the game and what's going on in the dialogue. And so what we do is we train the model to condition its dialogue generation on the state of the board. So we actually feed into the context the state of the board and the moves that we intend to make, and the moves that we would like our dialogue partner to make. And then by conditioning on those, it's able to have a much more grounded conversation where the dialogue is now reflecting what, we would like to move, what we would like to do strategically, and what we would like the other player to do strategically. So we have our reinforcement learning algorithm come up with like a good set of moves for ourselves and a good set of moves for what we'd like the other player to do, and then we condition the dialogue generation on that so that it's communicating with those intentions in mind. And you see that in the dialogue, that it will then say things like, I'm going to move this unit from here to here, or I'm going to support your unit moving from here to here. It can also, it's also much more human-like than that. Like, it will have, broad conversations about like, oh, I think this player is like getting really powerful and we should, work together against them. And so it'll have like these, pretty wide spectrum of conversations, but it will be much more grounded in what's actually happening in the game. And so that ended up working out surprisingly well. We actually played this game. We actually played this bot in an online diplomacy league with real human players. They did not know it was a bot. We didn't tell them it was a bot. And over the course of, I think it was like 40 games, the bot ended up placing in the top 10% of human players in the tournament, in the league. And surprisingly, nobody figured out that it was a bot over those 40 games. These games would last like hours, and it would have like, hundreds of back and forth conversations with these players. And still, they thought it was a human the whole time. And we actually told the players after the experiment completed that it was a bot, and they were shocked. They thought they were playing with another human the whole time. They didn't see anything suspicious about it. And that came as a big surprise to us. I mean, we were really concerned that like we would deploy this bot, and like within 2 games they might figure out that it's a bot, and it would ruin the whole experiments. But we had somebody constantly watching the games with their finger on this big red button that would shut everything down if like somebody started getting suspicious. So we could like intervene and try to salvage the experiment, because as soon as somebody figures out that there's a bot in this league, they're always going to be suspicious of bots after that point. But fortunately, that never happened, and the dialogue ended up being surprisingly human-like.
It's fascinating how well it can do in diplomacy. Diplomacy is very connected. It's about strategizing warfare. Obviously, not the goal, but seems like it would be similar to strategizing other things, business relations, maybe political agreements on things like, I don't know, climate accords and things like that. Have you given it any thought how what you built for diplomacy could maybe play a role in these real world negotiations and strategy developments?
Yeah, I mean, I think what's really cool about the game of diplomacy is that it's the most human-like game out there. I mean, I think you're communicating in natural language with real human players. You have to account for the fact that these are players that play emotionally, that they're not playing perfectly rationally like machines. And all those things end up forcing you to develop new techniques that do end up having applications to the real world. So I do think that techniques are really important for extending these AI techniques to the real world. I mean, that's always been the promise of AI, right? Especially when it comes to games. Like we justify the AI research on games by saying that, eventually these techniques will be applicable to the real world and that they'll have real world impact. I think what's really exciting is that we're finally starting to see that promise be fulfilled. And yeah, I do think that the techniques that we've used in diplomacy and the techniques that have also been used in poker to some extent will have real implications for the real world. Now, going right now to real world negotiations, I think it's hard. I think it depends on the domain. If you start looking at like international relations, like these kinds of negotiations, there's a lot of nuance and there's a lot that you have to understand about the world in order to contribute to those negotiations. In a game like diplomacy, it's relatively easy because everything you need to know about is on this board. Like there's a lot of personality stuff that you have to account for, which that's not easy, but we can do it. But as far as what you're negotiating over, that's all on the board. In this self-contained game. When you start going to business negotiations or international negotiations, you have to understand things about business models, things about the history of various countries. There's a lot more going on. So I think that isn't going to happen imminently. I do think that we will get there eventually, and I think that the implications will be pretty powerful. And I think it's worth trying to think about what those implications are now. I think the more likely path is that we'll see simpler negotiations being handled by AI in the near future, and then the level of complexity will grow over time. And there's certainly like certain kinds of negotiations where I think you could see AIs playing a role in the near future. I think negotiations over prices, for example, will probably be handled by an AI in the not too distant future, I think. So if you're negotiating over the price of a hotel room or the price of like an airline ticket, or, I think a lot of business to business negotiations over pricing, that will probably also be handled by AI in the not too distant future. And so I think that will be really cool to look forward to. And I think that will just make the economy much more efficient. I'm really looking forward to that. I think that has a lot of positive outcomes for the world. And then I think that the level of complexity will grow over time.
Very curious to see that all play out. Now, Noam, currently you're at OpenAI, and your current direction is planning, reasoning, and self-play in language models. So the big models like ChatGPT and so forth that many people, of course, have tried out, these kind of models apparently are going to have similar intelligence to them as what you put into the poker and diplomacy bots. Can you say more? What are the opportunities here and what are the challenges?
I think there's a lot of interesting research left to be done in language models. I think one of the things that I've taken away from the game space is the power and how effective it is to do planning in these games. So I mentioned, in Go, if you add planning, it's like the equivalent of increasing your model and training by 100,000x. And the same thing is true in poker. If you add search in poker, it's the equivalent of increasing the model size and training by 100,000x. And I think you can do something similar in language models. It's not really clear how you do it yet, but I think that there is an opportunity there. And I think this is really important because, if you look at the cost of how much it costs to train these language models today, it's really expensive. And we're going to see it scale up. I'm sure the models are going to get bigger and bigger and trained for longer, but you're not going to be able to scale them up by 100,000x, at least for the foreseeable future. And in a AI paradigm where scale is the key thing, there's a question of like, okay, well, if you can't scale up the model during pre-training beyond a certain point, then how do you scale it up further? And I think the answer is you scale up the amount of inference cost. Like the language models typically these days, they respond very quickly. If you ask it a question, it can give you an answer in milliseconds or, maybe seconds at most. But for a lot of applications, you don't need a response immediately. You can wait a minute or an hour or even a week sometimes to get a response. You can think of like, if you ask the model to write a contract for you, a legal contract, you don't need that in 5 seconds. You can wait like a minute for a really high quality answer. And, thinking like if you wanted to write a novel, that could take a full week. But I think, if it's, and obviously the inference cost would be a lot higher in that case, but if it's something like writing the next Harry Potter, then that seems totally worth it to spend, 1,000 times the inference cost, or to find a new life-saving drug, or to prove the Riemann hypothesis, or any of these things. There's a lot of applications where it would be worth it to spend orders of magnitude more on inference in order to achieve the equivalent output that you would get from a model that's orders of magnitude bigger. And so I think those are the questions that I'm interested in investigating and researching going forward.
Very exciting. Now, one could also argue that in principle, the training time is a one-time cost and inference has to happen for everybody. But maybe it's okay. Maybe it runs on your phone and you already own the phone, so you're not really paying much inference cost compared to doing cloud API calls to something. But it does seem like it might depend on somehow on how often you train versus how often you run inference. And right now, inference is run much more often, right?
Yeah, I think it absolutely depends on the domain. I mean, there's some domains where, you want to pay almost all of the cost up front and then have like minimal inference cost. And I think, a lot of, if you're doing web search, I think that's a classic example where, you're going to get tons of queries and you want responses as soon as possible. But there are other domains where, it's okay if you only run it a few times. And I think actually Go is a good example of this where, it's okay if the model takes 30 seconds to think about what its next move is going to be. And, in theory, you could move that all to pre-training, but then your pre-training is going to cost 100,000 times more. And so you'd much rather shift a lot of that burden to test time, beat the world champion once, and, that's fine. And like I said, if you're developing a life-saving drug, you probably don't need to develop 100 million life-saving drugs. If you can just generate 5, I think that would be a huge deal. And, writing a prize-winning novel, you might not need 100 million of those, but if you could just generate a few, then that would be a big deal. And so a lot of there's a lot of applications where if it's a trade-off between scaling pre-training by 100,000x or scaling inference by 100,000x, it would be worth it to scale the inference by 100,000x instead.
I love these examples. One thing that's on my mind related to this is video prediction. Because you're saying writing a novel, once you write the novel, maybe it can be turned into a full movie, right? Right now in video prediction, there's not a whole lot of time spent at inference either, so it seems like maybe the same thing could be true there, moving more compute into the inference cycles.
Yeah, I think that's absolutely right. I don't think this is limited to any particular domain. I think that it really is something that could be applied more broadly. Yeah, I think that's another good example. I mean, I think really the question comes down to the domain. Like, are there domains where you are willing to pay a much higher inference cost compared to the training cost? Now, I should say there's a lot of challenges that come along with this. I mean, in games, it's relatively straightforward. There's certainly questions around how do you do search in a game like poker. One of the nice things about a game is that you have a well-defined ground truth reward at the end of a trajectory. So if you play chess, you can do self-play. Eventually, you'll reach the end of the game and you'll know who's won and who's lost. In things like, language, it's much more difficult to say okay, well, there's these different paths that I can go down and which one is better than the other. That depends on how good your reward model is, or if you have good human feedback. So there's a lot of question marks around how do you carry these techniques over to these less clear-cut domains. But that's what research is all about, is figuring out how do you address these problems. And to some extent we encounter this in the game of diplomacy. In diplomacy, you don't really we have these models of how humans might play, but they don't really match up with how humans actually play. And so we had to figure out, how do we do planning in this game, even though we don't really know how it's going to carry over to the real world. And we were able to do that. And so I think that some of those techniques will extend more broadly. We might have to come up with new techniques too, but I'm looking forward to the challenge.
Switching gears, Noam, curious, where did you grow up and what got you excited about artificial intelligence?
I was born in Israel. I moved to New Jersey when I was 2 years old. Grew up there. And I'd actually always been interested in artificial intelligence from an early age. I started trying programming when I was 10 years old. Just, a little bit not too seriously. I just found somebody gave me a textbook on programming, and I tried to implement a few small games myself. When I was in high school, I took a computer science class, and one of the tasks was to program this game called, I think it was called Gomoku or something, where it's you have to get 5 in a row. It's kind of like tic-tac-toe, but you have to get 5 in a row instead of 3 in a row. And there was no AI component to that project, but I was really interested in like, could you make a computer player, like an AI for this game? And so it's just like kind of on my own, I started doing that, and I thought it was really interesting. You know, I ended up not going down. I majored in computer science, but I decided not to pursue AI at the time, in part because, you know, this was back in like 2009, 2010. AI was not a very hot thing back then. It was. I remember talking to, you know, various professors about like, what should I be doing with my career? And back then they were saying like, don't go into AI. AI is a dead field. Nothing's happening, and like all the techniques haven't worked out. I ended up actually going into finance. So I worked in algorithmic trading for a couple of years. It was really fun, but I didn't find it particularly rewarding. It's not what I wanted to do with my life. And it became clear to me within a couple of years after undergrad that what I really wanted to do with my life was research. Now, I didn't have any research experience in undergrad. And so obviously getting into a competitive PhD program without any research experience is not the easiest thing to do. So I went to the Federal Reserve for 2 years and worked as a research assistant, actually researching algorithmic trading in financial markets. And my plan was to do a PhD in economics. But while I was there, I realized what I really enjoyed doing was building things. I really enjoyed a lot of the computer science and statistics work, and I thought like a PhD in economics would be cool. But what I really want to do is a PhD in computer science focused on artificial intelligence and computational game theory. And you know, again, this was still in 2012. AI hadn't really taken off at that point, but regardless, I felt like this is what I want to do with my life. And I started the PhD in 2012. Actually started a master's first and then continued to the PhD. And conveniently, there was a professor that was looking for somebody to do research on AI for poker. And it felt like the perfect intersection of like all the things that I was interested in. I mean, I was interested in AI. I was interested in game theory. I had played poker in college and always enjoyed the game as, you know, kind of like the strategic aspects of the game. And so actually, even when I was in college, I decided as a side project to try to make an AI for poker. It did not work out very well, but it was really interesting and I had a lot of fun doing it. And so, you know, to think like, oh, I'm going to get paid, you know, for 5 years to be able to like work on this. It's like, I would do this for free. I'd like as a side thing, like, this is great. So I happened to, you know, end up at the right place at the right time. And, you know, we got very lucky in that respect. And fortunately, also, the whole field of AI blew up during my PhD, and that was great to see as well.
Yeah, very good timing. And I think, I mean, in terms of PhD, in my opinion, it pretty much has to feel like something you would want to do for free as a side project, because it's not like you're really getting paid during PhD, barely enough to make ends meet, right? And it's just, I feel like that's the big opportunity. It's 4 or 5 years to do the things that are just, you know, what you really want to be doing, assuming you find the right lab, the right advisor that, you know, where you have the right freedom to do exactly, you know, explore and do the things you want to do. Now, one final question, Noam. Obviously, you keep very busy. What are some things you do to relax?
Yeah, I have friends over for board game nights every once in a while, like once a week. Sometimes play poker casually. Never for very high stakes, usually just like $10, $20 buy-in games. You know, I'm really interested in the strategy and the psychology of the game rather than like, you know, the gambling aspect itself. Though I did actually recently play in a high stakes game with $20,000 buy-ins. I actually got bought in, fortunately, so I didn't have to pay that out of pocket. And ended up doing quite well. I ended up walking away with $40,000.
Oh.
That I split with the person that sponsored me, fortunately. So that was truly a once in a lifetime experience. You know, aside from those things, I try to keep in shape. I've gone into bouldering recently, as a lot of tech people do. And I'm looking forward to a lot of great traveling this year. ICML is going to be in Hawaii. I'm looking forward to that. And I'll be going to Ichikai as well in Macau.
Yeah, great destinations. Well, No, thanks so much for making the time. Really enjoyed this conversation.
Well, it was a great being here, and always happy to talk.